Good afternoon, everybody. Can you hear me?
Yes. Yes. Hello.
All right, thank you. Okay, so hopefully you all saw the key. And I did get a couple of questions about the grades. I just want to make sure everybody was okay with that. If you have any questions, you can email me. Right, let me know. Let me know if there's any questions anybody has. All right, so we're going to start on test 2. Now, if you look at the schedule here, you look at the syllabus, you'll see that test 2 is actually March 1st, which is really only 2 weeks away. But this test doesn't have as much material in it as the first one did. And I want you to realize that it's actually kind of a gift, because there isn't that much going on here with this test. So you'll see that when we, this PowerPoint, we'll go printable PowerPoint. And traditionally, people do pretty well with test 2. Now there is a naming quiz that goes on with this, and that's what we'll start with, will be some naming. And this test is going to be pretty much about, let's get rid of this. It's going to be mainly about aldehydes and ketones. So reactions of aldehydes and ketones and all of that. So we'll get started on this. So aldehydes have the formula C double bond O with an H, and ketones are C double bond O with a C. So typically, aldehydes are going to have this grouping on the end, whereas ketones are going to look more like that. So that's an aldehyde. And this is a ketone. Usually going to be pretty easy to tell. You might also see aldehydes presented like this as well, without the H shown, and that's possible as well. I mean, it is a line structure. We don't have to show H's, but if we do, they're often shown on aldehydes, just to remove any doubt that they are aldehydes. Now, when we're naming them aldehydes, they end in Al. So the suffix ends in Al. So this would be hexanal, 1, 2, 3, 4, 5, 6. 6 carbons. Let's see if we can increase the size a little bit here. And there's no need to say where the aldehyde group is, because it's assumed to be on the end, and we're numbering from the aldehyde. So in the next one, you can see it's 3,3-dichloro-4-methyl hexanal. So again, it's a hexanal because that's the longest chain. And then 1, 2, 3, that's where the chlorines are, and the methyl group is on the 4th carbon out from where the aldehyde group is. Does anybody have any questions about naming of aldehydes? Okay. Now, ketones end in the suffix ONE, and you'll see that because the ketone group could pretty much be anywhere in the chain except the end, then we need to specify where that double bond O is actually coming from. So for this one, it'd be 1, 2, 3, 4 octanone, and that's the smallest number we could make here by counting from the left-hand end. You'll notice we didn't do it from the right-hand end. So the other thing we need to take account of is the fact that the ketone will take priority. You know, where it is, that's what's going to take priority here. And this one here would be 1,1,1-trichloro-2-butanone. And again, well, you know, maybe in this case, if I was calling it butanone without the 2 there, I might actually get away with that, because there's no, well, I suppose it could be Could be over here, that would be different. But yeah, that's where the, yeah, so the 2 here is where it would be 1, 2 would be the numbering. When you got cyclic ketones, then we don't say where the double bond O is. We're assuming it's at number 1. Excuse me, sorry. Been holding that back.
Bless you. Bless you.
Thank you. This would be called cycloheptanone. You'll notice there's no saying where the ketone group is, because it could be anywhere there and it'd be fine. In this case, we're looking at the direction that would give the lowest possible numbering, but the 1 position is always going to be the C double bond O. And if I was to number it in the other direction, then it would end up that I'd end up with higher numbers than if I did it in the direction I have done it, which is clockwise. I could have tried to number it counterclockwise, but I'm going to find those numbers will be larger. Does anybody have any questions about the naming of ketones, either cyclic or otherwise? Okay, you'll find, I think, that the naming quiz for this one is going to be a little less cumbersome than the naming quiz for the other one. So let's take a look at it. I don't think you can mind this one as much as you did the other one. You still get a large number of attempts, so it's the same kind of thing. You know, you'll be given either an aldehyde or a ketone. You'll have to name it. Same kind of deal as before. Does anybody have any questions? Okay. Just make sure you read the directions on the quiz before you take it, and that will give you a good idea of the guidelines you need to follow. You can see them all here. Just make sure you read those. All right, does anybody have any questions about naming or the naming quiz or anything like that?
Is the naming quiz timed? I can't recall.
It is.
It is, okay.
Yeah, but you should get a couple of minutes per problem, I think.
Okay.
It should be. It's open book. All right, so there is that.
There is that.
So for the aldehyde, we always number the chain where aldehyde gets number 1,
yeah,
regardless of
yes.
whatever group is attached.
That's true, Mariam, yes.
Okay.
Yeah, so don't go for lowest numbering set, even if that's true. The aldehyde will take precedence.
Okay.
Just like the ketone would in a ring as well, right? All right, so let's look at synthesis of aldehydes and ketones. So let's first of all look at oxidations and reductions. So what usually characterizes oxidations is the gain of oxygen and or loss of hydrogen. And the other thing we tend to see with oxidation is an increase in the bond order. So we might see single bonds going to double bonds, going to triple bonds. Those are oxidative processes. Reductions tend to be loss of oxygen and or gain of hydrogen. And the other thing we see there is a reduction in bond order, going from triple bonds to single bonds, double bonds to single bonds. So that's something you can look to determine if an oxidation or a reduction is occurring. We're going to start out with oxidations here, and oxidations specifically of aldehydes. Now, aldehydes can be made, because they're on the end, remember, they'll be made pretty much from primary alcohols. That is, alcohols where the OH is on the end of the chain. And you'll see that there's an oxidative process that we can do, and that's what the O in the square brackets is. That means oxidative process. And you'll see the pattern here. We've got two hydrogens here that are attached to the C that has the OH on it. And when we do the first oxidative process, you'll notice that it turns from a single bond into a double bond, and we lose one of those hydrogens. And then in the next oxidative process, it turns the aldehyde into a carboxylic acid. So the magic here in forming the aldehyde is doing it in such a way that we just do one oxidative process and not two oxidative processes, because if we do over-oxidize the aldehyde, it'll turn into a carboxylic acid, which isn't what we want. So what we have here is a situation where if we do it with a mild oxidizing agent like PCC, it'll stop here at the aldehyde. But if we use a harsh oxidizing agent like CrO3, it'll go straight to the carboxylic acid. So using a mild oxidizing agent will allow us to stop at the aldehyde. If you look at what PCC looks like, it's this pyridine ring, this ring here, with CrO3 attached to it. And that's kind of like a complex is what it's called. CrO3 is joined to this ring. And then if there's no ring there to kind of calm it down, then it's just CrO3. You can see it's just going to turn into a harsh oxidizing agent, and away it goes. All right, does anybody have any questions so far? Okay, so PCC, or pyridinium chlorochromate, is a mild oxidizing agent and allows us to take a primary alcohol and turn it into an aldehyde. To make a ketone, it doesn't matter what oxidizing agent you use, because in my view here, if it's a secondary alcohol, and what that means is there's only one hydrogen that's available to be oxidized away. Go back to the previous one here, and you'll see there were two possible hydrogens that we could oxidize for the primary alcohol. Whereas for the secondary alcohol, there's only one hydrogen that we can oxidize. And it doesn't matter which oxidizing agent you use. You could use PCC or CrO3, and you'll end up with the same product. But the key for a ketone is that you are starting with a secondary alcohol. All right, so let's see how we tell if an alcohol is primary or secondary. In the case of primary alcohols, the OH is at the end. And in the case of secondary alcohols, the OH is in the middle of the chain. So here are a couple of examples. These are primary alcohols that you're seeing here in the summary at the top. PCC will turn it into an aldehyde. Remember, you can show the H or not show the H. If we use CrO3, it'll go all the way through to the carboxylic acid. In the case of secondary alcohols, it doesn't matter what oxidizing agent we use, we'll end up with the same product. Does anybody have any questions?
What happens with tertiary?
Let me see. I thought I might have shown this here. Well, tertiaries have 0 hydrogens in the oxidative position. But I don't think I have it anywhere here. I thought I had it, but I don't. But they have 0 hydrogens in the oxidative position. So if you look at a tertiary alcohol, it'll look like this. So you'll notice there's no hydrogen here. So it wouldn't oxidize in a way that would allow us to get anything that we would want.
Okay.
All right. Any other questions? So when you're doing problems that involve alcohols and you're trying to determine what kind of product they're going to be to give, you have to really look at what kind of alcohol it is. Is it a primary alcohol or is it a secondary alcohol? And since we're dealing with aldehydes and ketones, I'm doubtful that there are too many problems where you would get anything but an aldehyde or a ketone as a product on a test, for example. All right, any other questions? Okay. So this is, I know we dealt with some mechanisms in the last test, and a lot of you did pretty well with them. But I'm going to really sort of hit them pretty hard in this test. And I think it's a good place to do it because there aren't that many reactions in this test. We might have like 12, possibly 13 reactions we're going to deal with in total. So it's not going to be a huge burden on you here. And then you'll see the value of learning the mechanisms and how that can prevent you from having to memorize a whole lot of stuff, because you'll be able to see the stories the arrows are telling you. So when we're dealing with mechanisms, we're always looking at the movement of electrons. So you'll find typically that arrows start at centers of negative charge and go towards centers of positive charge. When we're trying to express a bond forming, there's two ways we can do it. We can have the electron come from the X and go to the Y, or we could even have the electrons come from the X and go into the space between the X and the Y. The story we're trying to tell there is two electrons from the X are being used to form a bond with the Y. Does anybody have any questions so far? When doing bond breaking, the tail of the arrow always starts in the middle of the bond and goes to one of the atoms, generally the more electronegative of the two atoms. So those are it. I mean, these two are interchangeable. You'll see me use both methods to express bond forming. And bond breaking is the arrow coming from the bond and going to an atom. That's it. Those are the only two arrows we really have to do. Those are the only two situations we really have to do with. All the other situations we deal with are going to be combinations of those. So you can see this one here, double bond forming. I've included this one in double bond breaking because we often see this in aldehydes and ketones. And you can see the double bond forming would be from the electrons in a YZ bond here being used to form a double bond, which is really just a combination of bond breaking and bond forming, bond breaking here and bond forming here, but happening simultaneously. And the double bond breaking, you can see, comes again from the bond and goes to a Z plus, and then the X gets the positive charge and the Y, if it bonds to the Z, ends up not changing its charge. But you'll see that this kind of looks like a hinge. It's like a door that opens. Think of it that way. And the X ends up losing electrons and the Y doesn't end up losing any electrons. Does anybody have any questions so far? So in the first few of these, I'm really going to hit the mechanisms fairly hard. And then sort of as we go through, I'm not going to be talking about the mechanisms quite as much, but I will be doing a lot of mechanisms, and you'll have to understand the stories that the mechanisms are trying to tell. There are students who will refuse to even have anything to do with mechanisms. They'll just want to memorize products rather than learn how to do the mechanisms. But learning how to do the mechanisms will form a great foundation. In fact, a lot of people who've already learned the mechanisms from Organic 1 are really reaping the benefits now when they're doing Organic 2, especially those bonus points that you get on the test as well. So when we're looking at the general mechanisms for aldehydes and ketones, you'll see they kind of fall into two categories. There's an acidic mechanism, which uses H+, and that's what I mean by acidic. And generally what happens is the H+ adds to the C double bond O, the H joins to the O, and the positive charge forms on the C at the bottom of the C double bond O. And then some nucleophile comes in and then that leads to products. Or the basic mechanism involves something negative coming in and directly attacking the C double bond O, and then the electrons jumping up on the oxygen, and then that leads to products. So those are the two situations we're going to be dealing with here. I find the basic mechanisms tend to be a little bit simpler than the acidic ones. You'll see that as we go through. So we're going to start out here with the reactions of aldehydes and ketones. And the first one we're looking at is called hydration. And for this, we've got an acidic mechanism and a basic mechanism. You'll see the products of both of these are the same. One uses H plus, one uses OH minus. So when we're dealing with the acidic mechanism, I'll show you an example of this. So you might see H2O, H plus. You might also see H3O plus. That might be a possible way you might see that expressed as well. They mean the same thing. And the product there is what we call a gem diol. It's a two OHs connected to a C. These are very unstable, by the way, and I'll show you on the next slide how stability of this kind of situation can be increased. But for the most part, this doesn't go very far in the diol kind of direction. It pretty much stays mostly with the aldehyde, but we can do this by doing this mechanism. So if we've got a choice here, let me put it another way. If we've got H2O and H plus here, the H plus is going to be the more unstable of the two because it's the one that has a charge on it. So that's usually going to be the one that reacts first. So that's how we would show the first arrow. Now let's look at the story this arrow is telling us here. This arrow is trying to say that two electrons are being taken from this C double bond O, which means we're going to lose one of these bonds. The H is going to join onto the O, but effectively what's happening is that these two electrons are being used to form this new OH bond, and this carbon here is effectively losing an electron, which means that the positive charge gets transferred to that carbon atom. So the positive charge that was on the H is now on the C. Does anybody have any questions about that first arrow? The next step involves an O joining to the C plus, and this will something is slowing down my computer here. I'm not sure what it is exactly. This is terrible. Let me see what the problem might be. I'll stop the share for a second. Okay, I should close down some processes. Hopefully that'll speed things along here. Okay, I'm also going to go blow my nose. I'll be back in a second. All right, sorry about that. Okay. So in the next step, excuse me, we're looking at having something attack that C+. Now, what would that something be? Well, it has to be the other thing we haven't worked with yet, which is the water. And the water, if you look at the structure of water, consists of oxygen, which we consider to have a delta minus, and hydrogen, which we consider to have a delta plus. And the oxygen is more electronegative, and it's considered to be the electron source here. So the O will be attracted to the plus, and you'll notice what the arrow is doing. It's coming from the O and going to the C plus, or the space in between the two. Which means now the oxygen has donated 2 electrons to that bond, so it becomes positive. The carbon has lost a positive charge now. And then in order for this reaction to complete, the bond to the hydrogen here will break. It doesn't matter which one, obviously. It could be either one. And again, look at where the arrow is coming from. It's coming from the bond, and it's going towards the O because we're looking at where the electrons are going, not where the hydrogen's going. It seems counterintuitive, but you kind of get used to it after you've seen it a few times. And that leaves H plus as a product there as well. So it's kind of catalytic. I mean, the H plus is there at the beginning. It's also there at the end. Does anybody have any questions?
I have a question. So
Yeah.
the last step where the bond between oxygen and hydrogen break, what happens is that another water molecule comes and take that hydrogen.
You could look at it that way.
I
tend not to show that, Miriam. I think it's a little bit. I'd prefer to keep it a little bit more simple than that.
Okay.
But yeah, you could look upon that from another water coming in. But I'm hoping you can see why I don't show that. I don't show it because I don't want to overcomplicate what really is a fairly simplistic situation. But if you wanted to include that water coming in, have at it.
Okay. Thank you.
But you're right, something does have to take that hydrogen. But I'm always assuming that whatever is in there to take it will be able to take it. Now, I'm not going to show an example of this one, but the basic mechanism here, you have the OH minus come in. It attacks the C. Well, actually, I'll show a little bit here. The product is the same, but when you've got the C double bond O, the polarity is always like this. Delta plus on the C, delta minus on the O. So anything that's negative will come in and attack the positively or partial positively charged carbon, and that's what's going on here. So if we did have this situation, that would be the first step. OH minus would come in, and then the electrons would jump up on the O. And you'll see that that's how it maintains having 4 bonds as well. But you'll see that the O now gains a negative charge that was on the OH, because now the electrons that were in the C double bond O are now on the O. So the O actually owns an extra electron it didn't have before. Then in the next step, the negative can take an H away from water, and that's how we end up with our product. So 2 fairly distinct kind of mechanisms here, depending upon if we're dealing with acidic or basic conditions. Does anybody have any questions? So these are the hydrate examples that I was just talking about. We've got the first one here, which was using H2O and H plus or H3O plus. And I showed you also that the C that's on the C double bond O will have what amounts to a partial positive charge on it. You'll see though that when we look at the equilibrium arrows here, that the equilibrium arrows go mainly back to the reactant. And we only have a very short arrow here going towards the product. So maybe in this kind of situation, you might have 99% of what's going on in the reaction being reactant and only 1% being the product, because that's where the equilibrium lies. However, if you were to put 3 chlorines on the carbon next to the C double bond O, then you would also be imparting a delta plus charge on that carbon as well. And you can see that in the next diagram. So because we've got the delta plus here on the C with the 3 Cls and a delta plus on the C double bond O, whenever we add H3O plus to this, you can see that the equilibrium kind of shifts more towards the product side. And the reason for that is because as a reactant, these 2 delta pluses are interacting unfavorably. It's kind of like a positive being next to a positive, which is not a good situation. And here, this actually doesn't have a very strong delta plus. I know there's 2 oxygens connected to it, but the C double bond O is a whole lot more polar than even 2 oxygens connected to the same C. Does anybody have any questions? So chloral hydrate is this compound here. It used to be used as an anesthetic. I don't think it is now. This is called chloral, which is the precursor or reactant. So the next one is cyanohedrons. This is one we don't tend to do in the lab because we have to use hydrogen cyanide, which is a little bit on the toxic side. So I'm going to actually show you 2 examples here of these kinds of mechanisms. So HCN will form the OH connected to the same C as the CN. And I'm going to show you 2 mechanisms because we can really do this either way. We can treat this as an acidic mechanism, in which case this is different to what I'm showing you here. In which case we add the H plus first, and then the CN minus comes in. But again, look at the direction of the arrows. The Cn minus is the one where the arrow is coming from because it's got the electrons on it. I'm actually fine either way, whichever one you want to do. So the other one has the Cn minus coming in first and the electrons jumping up on the O. And then we have the H plus adding to the O here. Does anybody have any questions? So the cyanohedron itself that has the OH and a CN group can be used to make amino acids. So the OH can be replaced with an NH2, and then the CN can be hydrolyzed to a carboxylic acid, which produces an amino acid. So this is a good way you can make pretty much any amino acid this way. Does anybody have any questions? Okay, so we're going to now look at reactions of hemiacetals, acetals, and hemiketals and ketals. This is something that's fairly important when we're dealing with carbohydrate chemistry, and we're looking at the reactions of glucose and cyclizing and uncyclizing glucose. So let me show you an example of that. So what you're looking at here, this is a C double bond O. Whoops. Oh, I don't. What was that for? Am I not hearing people?
No,
No, you're fine.
So how? So where'd that chat message come from?
Somebody asked me something and that was my response. I thought it was going to that person and it went to everybody. I'm sorry.
Oh, okay. I get it now. Okay.
It's a compliment to
At
you,
least
though.
it was a nice comment, and it wasn't.
Exactly.
I think Dr. Musgrave's a bastard.
Yeah.
That would.
I hid those better.
Yeah, that's good. Yeah, you've got to be careful with those. Sometimes you can put the good ones out just as like fodder. Just.
Well, exactly.
Yeah,
I keep
yeah,
you
sort of.
misled.
Yeah, that's right. Okay, so this is an example of, in this case, it would be, or hemiacetal formation, because this is an aldehyde and then an OH group is reacting. So this is an important biological process because glucose actually comes in two forms. It comes in a cyclic form and an acyclic form, and it turns out that this cyclization here is a reaction of an OH with an aldehyde group. In the case of a ketone, this is the OH, this forms a hemiketal, and it's an OH reacting with the C double bond O. It gets me thinking now. There must be all these little conversations, side conversations going on through chat, and I have no idea about them. It's all a little bit scary.
That was actually the first chat I've ever had in your lab.
Oh, okay.
I did it badly.
All right. So whether we're talking about hemiacetals, acetals, hemiketals, or ketals depends upon what we're starting with. If we're starting with an aldehyde, then the addition of one alcohol equivalent will produce what's called a hemiacetal. and 2 alcohol equivalents will produce an acetal. Hemi is a prefix that means half, like hemisphere, for example. Ketone. A ketone starting with alcohol, 1 mole will produce a hemiketal, and then 2 moles will produce a ketal. You don't need to know these names. I'm just telling you them because they do relate to what we were just talking about, to carbohydrate chemistry. So let's look at hemiacetals and hemiketals. The situation is pretty much identical as far as the mechanisms go. And I'm really going to focus mostly on the positive mechanism and not so much the negative mechanism, the positive one rather than the acidic one rather than the basic one. So when we've got, say, this aldehyde here, and we add an alcohol, you'll see it's going to be pretty similar to what we did last time with the water. And the product here, instead of being 2 OHs, is going to be the alcohol group adding on, and then an OH group will be on the H here. So that would just be 1 mole, or if you like, 1 equivalent. So the mechanism goes something like this. The H plus will add to a C double bond O first. You'll see this happen again and again, by the way. And then we can add our alcohol group. And again, look at the direction of the arrow. It comes from the O and goes to a C plus. And then we can lose the H off the O plus. But again, look where the arrow comes from. It comes from the middle of that OH bond and goes on to the O. All right, does anybody have any questions so far? So that would be what I'm calling a hemi, in this case, hemiacetal. And that was with just 1 equivalent of alcohol. Now, if we're dealing with an acetal, what we're doing then is we're taking the aldehyde and adding excess, or well, effectively 2 moles, but excess alcohol. And the product then looks like this. 2 alcohol groups end up connecting to the C that had the C double bond O. So let's look at the mechanism for that. This one's sort of getting more into a realm of what we're looking at on the test as well. So C double bond O adds to the H plus. And then we have the alcohol group joining on to the C plus, just like we did previously. Now this next step is a bit of a convergence, or sorry, divergence from what we saw in the last mechanism. And what I would say here is, if you know what the product is going to be, then you can see that there is no OH here. And generally speaking, if something's going to leave, it tends to need to be protonated. It tends to need to get an H plus on it. In order to achieve this, one method is by using what I'm calling a proton transfer, where the O from the OH group that we know is going to leave will take the H off the O plus. in a single step like this. So if you want something to leave, protonate it. You'll see this pattern again and again as well. And then the group leaves once it's been protonated. And then the other alcohol group can come in. Whoops. The other alcohol group can come in. And then the H plus can be pulled off the O. And that gives us our product. All right, does anybody have any questions?
I do.
Next slide here. Yeah, Julie.
Oh, Deanna.
Oh, sorry, Deanna, sorry.
It's okay. So, I don't even know. What's that P where you use protonation?
Protonation, yeah.
Protonation. So the protonation part, that that arrow is going from the O to that hydrogen.
Yeah, forming a new bond between that O and that H, yeah. Now, it looks like that's going a very long way to do that, but it actually isn't. If we look at this in 3 dimensions, the situation looks a lot more like this than anything else. So you've got the OH. This O and this H, they're actually not very far apart in space, really. So it can kind of grab that. Because it's in 3 dimensions. It's just hard to show that in 2 dimensions. Okay. Any other questions? So this is, sorry, go on. Miriam?
How do you know what's supposed to leave? So you protonate that to make it leave.
Okay, so my point is that if you've got to know what the product is, Miriam. So if you know what the product is, that it doesn't have, where are we here? That it doesn't have an OH on it. You see that? Look at the product. Yeah. So you know that group had to leave, right? So the way it would leave is to be protonated. And if it's protonated, it can leave.
Okay.
And you'll see this pattern happen again and again. And most of the time I'm going to justify it. Now, but because we know what the products are. We always know what the products are, Miriam. So it's a matter of being able to explain how we're getting to that product. And we're doing that by using the mechanism.
Right.
So what you'll see this also when we're doing the test as well. Whenever I'm asking a question that requires a mechanism, I always give you the reactant and the product. And if it's a bonus question, then you know that's when you have to come up with the mechanism without the product.
Okay. Thank you.
Okay, you're welcome. Does anybody have any other questions? So the other thing that we can do is go in the reverse direction as well. And we can hydrolyze. We can hydrolyze an acetal. And what hydrolysis does is it turns the acetal back into the aldehyde from which it from whence it came. And that would be plus 2 equivalents of alcohol. So this is what this thing here is methanol, by the way. So it's CH3OH, just in case anybody was wondering. It's not like an OH negative or anything with a very long line. Hoping people realize that. So the first step is the addition of the H plus to one of these oxygens. It doesn't matter which gives the H on the O plus. Now, since this has just been protonated, what's going to happen? Something's going to leave. I mean, look at the product. You can see that both of these groups are gone, right? So that was the point I was trying to make before, Miriam, as well. So that leaves, leaving the positive charge on the C, and then water can come in. And then we'll still have an alcohol group attached still. Now, if I want this alcohol group to leave, which I do because I can see that this doesn't have any alcohol groups on it, then I can do this proton transfer and have the O grab a hydrogen off the water here. And then I kind of like to do this. Actually, I'm going to do it this way. I kind of like to do this last step as a combined step, because I think it really does probably happen that way. And this allows us to get the C double bond O to the hydrogen, and then the other alcohol group with the H plus as well. So you'll notice that the net effect here is that we've lost 2 alcohol groups, but you'll notice that I didn't have to show them both at the end. I should have shown this one. Yeah, when this one left, I should have shown it over here. So yeah, that's when that one left. And then we had the line to the OH there as well. So that's that first alcohol group coming off. So we don't have to show it at the end. It kind of gets shown along the way, and that's the way mechanisms usually go. Does anybody have any questions?
In the product you have, is that plus 2 OH? But in the product, after all the mechanisms, you have an H plus and an OH.
Well, that's what I was saying. That's what I was saying, Donna. This first thing with the OH on it was appeared here.
Okay.
And then it appears here at the end. That's the second one.
Okay. And we don't care about that H plus?
Well, the H plus is catalytic. It was here at the beginning. It was here at the end as well. But there it is on the arrow.
All right. Perfect.
Okay. All right. So now we're moving into the realm of one of the things you'll have to do on the test, which is a mechanism. And it's either going to be one of 2 things. And I'm going to show you, be very clear about the 2 possibilities that we're going to see here. We can look at a cyclic acetal formation. Which is going to take the form of this kind of thing, but not necessarily this particular compound. Plus H2O, or we can go the other way as well, cyclic acetal hydrolysis. And you could get either one of these on the test. So that would be the acetal using H2O and H plus turns into, or the ketal or whatever it is, turns into that plus the ketone or aldehyde plus this diol compound here. So it could go either way, right? Those are the two possibilities. So I'm going to show you examples of both of those. I'm not going to use this example here. It's a bit more complicated than I want to do. So we'll look at cyclic acetal formation first. And the first one here would be, let's see, just an example. Now remember, whenever you're asked to do a mechanism, I always give you the reactant and the product. So I think, Miriam, your question earlier was basically, how do you know what's going to happen, I think, was part of it. And part of the reason you know what's going to happen, I don't need to have H plus there, is because you have the product and you know what has to come and go. So let's see how we can sort of predict what's going to happen here if we have everything in front of us. So the first step is going to be the H plus adding to the C double bond O. And then the next step will have the OH, or one of the OHs, from the diol here, adding to the positive charge, or the C with the positive charge here. Now, if we look at how that goes in the mechanism, just look at what the arrow is telling you. The arrow is saying we're joining the O to the C plus. And then that puts a positive charge on the O like that. Does anybody have any questions so far? Now, a fair question would be, well, how do I know that's going to happen? Well, I'm looking at the product and I can see that somehow this has to join on to that specific C. So that's a reasonable or logical thing to do in the first instance, is to have one of the O's from the reactant, the other reactant, add to the C plus that we're forming with the H plus. Does anybody have any questions so far? Now look at the product. You can see it doesn't have this OH on it. So it's reasonable to say, well, this OH is going to have to disappear. So what's going to happen? Well, the OH is going to want to leave, and the way it can leave is by doing a proton transfer. I don't like that so much. Let me see if I can draw it out a little bit better. That's better. Nope. Let's try it again. That's better. Okay. And then I don't have a very long bond here. There we go. It's better. So the O will join on to the H, and then the bond between the OH here will break and the positive charge will go away. It'll go on to the water up here. Then the water can come off, and that's how that OH group ultimately leaves, leaving a positive charge on that C. And then the O from the other alcohol portion will add to the other end there, and then we can lose the H plus, and that forms our product. All right. Does anybody have any questions?
Just give me 2 seconds to finish writing.
You understand I'm recording this, right, Donna?
Keep going.
Yeah. Okay, well, I'll leave another minute here before I continue. Anybody have any questions?
I do. Can you just explain like the last arrow?
Okay, so the last arrow is coming from the OH bond and going on to the O. And the reason we're doing that is because, well, O needs only 2 bonds, and we're expecting the electrons to come from the OH bond and go on to the O to satisfy the positive charge. So the H becomes H plus because it loses an electron once that bond breaks.
Got it.
Okay. Does anybody have any questions?
I have a quick question. I'm trying to see why does OH, I guess maybe you mentioned it earlier, why does OH makes that circular motion to the bottom OH, to the bottom bond between O and H? I guess I'm asking what is attracting that OH to go there?
Okay, look at the product. You see there's no OH at all in the product?
Could you point it? Where am I looking? Oh,
Here.
okay.
Right, no OH there at all, right? So it must have left. And my justification is if it's left, it's because it got protonated. It picked up an H plus from somewhere.
Okay, okay.
And it kills two birds with one stone. We know that this O needs to lose the H, right?
Mm-hmm.
And this needs to gain an H plus.
Mm-hmm.
And then it leaves. See, look what happened. As soon as it gained that H plus, what did it do? It left, right?
Yeah, yeah. Okay.
And that left a positive charge on the C, which allowed the other O to join.
Yeah.
Okay, any other questions?
And when the H2O listed there, like when it leaves, do we have to put H2O, like show it leaving, or just that's fine with the mechanism showing it's going there and it's assumed it's left and at the end?
No. Actually, I should have done that. I should have put the H2O here. You're right. Thanks, Peter. Should have been here. Thanks.
Okay, I just didn't know how much you wanted to show there. So
Yeah, well, it has to be. Well, that's the thing. If I'm going to show this mechanism completely, then I have to show exactly what's happening in each step, which means showing, what's leaving and what's going on at each particular juncture. Yeah, I'd forgotten to add it, so yeah, there it is now. Okay, any other questions?
Can I ask something? I mean, I understand what you did here, and I get that we need to look at the product. I'm saying, would I get a different product if my oxygen would attack the hydrogen on the OH, the other primary OH that that doesn't have a positive charge?
No, it couldn't. It couldn't, because this oxygen here wants to become neutral barium. So and this doesn't want to gain a charge. That would have to gain a negative charge to do that. That's not going to happen.
Okay. Thank you.
All right. Any other questions? Okay. All right. Well, let's look at the reverse process then, and that would be acetal hydrolysis. And that would be taking, well, we'll take the same thing as we just used, I guess. Taking that acyclic acetal, turning it back into a ketone, and the initial diol as well. Ooh. So the first step will be the H plus attacking one of those oxygens. It doesn't matter which. And then look what happens once it gets protonated. It leaves. But by leaving, though, what I mean is it's still kind of attached, but the OH group is now no longer attached to where the C plus was. And then the H2O can come in. And that attacks the C plus. Which leaves a positive charge now on that oxygen that's part of the water. And the rest of it hasn't changed. Now we know also by looking at the product that this group is no longer attached to the carbon chain. So we know that that's going to get protonated. And then I don't mind this being shown in one step here. The ketone reforms and the leaving group leaves, and we're left with our product, which is actually the ketone and H plus and the alcohol. Let's see, where did the waters, nothing else came up here? That's all right, I think that's good. All right, so that's it for that one there. So you get possibly either one of those, either the cyclic acetal formation or cyclic acetal hydrolysis. Does anybody have any questions? Well, since we've got a couple of minutes. Now I've gotten, well, I haven't got keys for fall 2009 or spring 2011. So if somebody wants to come up with keys for those, I'll grade them and I'll put them in. I'll put them in here. All right, so I'm telling you straight up, I don't have them. Okay. But if you could please make that happen, then I will add them in. So let's have a look. I'll look at fall 2009 just for kicks. And the question I'm referring to here that has the cyclic acetal question would be, in this case, I think it's question 3. There you go. And this one was cyclic acetal hydrolysis. So as you can see, that's an example. But it could have gone the other way as well. It could have started with these and ended with this one. All right, does anybody have any questions? Okay, well, we'll leave it there for today and we'll continue with the fun on Thursday. All right.
Thank you.
All right, I'll see you guys later.
Thank you.
No worries, thank you.